Alright, this problem is still an equilibrium problem, but it's involving Q and it's converting between KC and KP. So it's kind of a all over the place type of problem. So we're going to start working it, and then I'll bring in an extra sheet of paper as we need it. So we're going to work on A. We're given the value for Kp, and remember Kp is equilibrium of pressure. And the question is Kc equal to Kp, Y, etc. So when we relate Kp to Kc, remember Kp is equal to Kc times RT raised to the delta N. So the delta N is the first thing we have to find. So we're looking at it, and remember we're only going to look at the gases. So delta N is equal to 4, 3, and 1 minus 2, which is 2. So because delta N is not equal to 0, Kc is not equal to Kp, so we have to calculate Kc. So what we're going to do is we'll come down here and we'll say Kp is 7.7 times 10 to the 24th is equal to Kc times R, which is 0.08206 liter atmospheres per mole K. Now remember, K is going to come out with no units. The advantage of putting it in here is to remember that temperature has to be in Kelvin. So 25 degrees C is 298.15 K. So we're going to do 298.15 K. Now, my K's cancel, life is good, and we're going to square this. So in this problem, we have 7.7 times 10 to the 24th is equal to Kc times 24.45388 squared. So that's 7.7 times 10 to the 24th is equal to Kc times 597.2247. So we're going to solve for Kc, which is equal to 7.7 times 10 to the 24th divided by 597.992247. So our Kc comes out to be 1.2876 times 10 to the 22nd, which is 1.3 times 10 to the 22nd. Okay, so Kp was large, Kc is still large, and that mostly means that this reaction is product favored. Because remember, K is always products over the reactants, so therefore, since K is so large, it will be product favored. If it had been really small, it would be reactant favored. Alright, so we've got our Kc value, so we're done with A. So just out of sheer meanness, I'm going to rewrite Kc up here so that I can always reference it. It's 1.3 times 10 to the 22nd. Now, we're going to start a second page here so that I can write again where we were at before. So this is 1, this will be 2, we may need to go to 3. So we have in B, a 6-liter flask is sealed with exactly 5 moles of each component. Is the system at equilibrium? Well, I don't know. If we know that we have 1 of each component, then we're going to have to figure out which direction is going to shift. So I'm going to rewrite my equation so that I can make an ICE table. Now, right now, whoops, I forgot the CO, plus 3H2. So we have I, C, and E. Well, initially, we know that all the concentrations are the same, and the molarity is going to be 5 moles divided by 6 liters, which means that all of the concentrations are going to be 8.3 repeating. So this is 0.833 repeating, 0.833 repeating, 0.833 repeating, 0.833 repeating. Now, we've got to change it. So before we can change, we need to know which way it's going to shift. That means that we have a Q problem. Q is equal to CO times H2 cubed over CH4 H2O. We're going to plug in what we know. It's 0.833 times 0.833 cubed over 0.833 over 0.833 to 1. So my Q value comes out equal to 0.6889. So that's Q. So the question then becomes Q's relationship to K. Well, Q is 0.6889. K is 1.3 times 10 to the 22nd. Okay, well that's a humongous difference. So we can honestly say that Q is less than K. If Q is less than K, then that means that we have too many reactants. We need more products. So the shift is going to be to the product side. So you're like, okay, how does that help me? Well, that means that when I go back up here, I can say we're going to shift to the product side. So I'm going to lose X here, lose X here, gain X here, and gain 3X here because there's a coefficient of 3. So we have 0.833 minus X, 0.833 minus X, 0.833 plus X, and 0.833 plus 3X. So we've completed our ICE table, which technically we were done with B when we did this part here. This got us where we needed to go with B. But if you'll notice, C says, what are the equilibrium concentrations of all species from part B? Set up through the equilibrium expression, include the ICE table, but do not solve. So we've actually set up the ICE table, and let's set up the K expression. So equilibrium is K. It's equal to product, which is 0.833 plus X times 0.833 plus X, plus 3X cubed over 0.833 minus X times 0.833 minus X. Okay, now a binomial was bad enough, and we actually do have a K value, so I'm going to put it here. A binomial multiplication was bad enough, but I do not want to cube that thing and then have to multiply by a binomial. But if I go back up and double check my problem, it says set it up but do not solve. So this part here would be part C, this would be part B, and I'm done with this problem because the math gets onerous. Could you do it? In theory, yes, given enough time. In a test situation, we don't have that much time, so I'm going to ask you just to set it up, but not to solve it.